Okay. Hi guys, this is Jan from DoraHacks and welcome to the workshop of our Hack AVS Empower the Eigenlayer ecosystem. So today is workshop number 7, which is about self-deploy and AVS using the Othentic stack. Before we start, let me give you some background of this hackathon. As the largest Web3 multi-chain developer incentive platform, it's an honor for DoraHacks to support and host the Hack AVS hackathon. We're looking forward to seeing all the amazing projects building on top of Eigenlayer. And today we're very happy to have Yotam, engineering lead at Othentic, here to share more about their stack. So without further ado, let's welcome Yotam to start. And for the audience, if you do have any questions in the meanwhile, feel free to drop them in the comment section and we're happy to answer them later.
Okay, thank you. Thank you very much, Jan. Happy to be here, excited to be here. Okay, guys, so my name is Yotam. I am leading the engineering team at Othentic, and today we're going to talk about how you can self-deploy an AVS using the Othentic stack. So we have quite a packed agenda, so I'm just going to run through the agenda real quick here. So I'm going to talk a bit about what is the Othentic stack. Then I'm going to talk a bit about proof-of-stake networks, and I'm just going to give a really high-level overview of proof-of-stake networks and how they operate as it relates to AVSs and the Othentic stack itself. Then I'm going to talk about AVSs specifically, so AVS networks and the similarities between AVS networks and proof-of-stake networks. Then I'm going to go over the stack components that come with the Othentic stack. I'm going to also give a really brief overview of what we call the anatomy of a task. So what is a task in the context of shared security and eigenlayer and AVSs. And at the end of after the slides, I'm going to show a couple of demos of our Othentic CLI, which is the tool chain that you use to deploy your AVSs and register operators and all of that good stuff. So let's jump in. I'm going to start with talking about what is the Othentic stack. So Othentic basically lets you leverage Eigenlayer's protocol in order to build proof-of-stake networks. Okay, so the Othentic stack is basically a framework that helps you build validated off-chain networks, off-chain computation networks. And it's a set of building blocks. So it comes with all those different components that you would need in order to build your own AVS network. And you can pick and choose which components you want to use. So basically, you can think about Othentic as a toolchain that lets you bridge the gap between Eigenlayer's on-chain protocol and your own decentralized service that you want to build. I'm going to start by talking a bit about proof-of-stake networks. So let's start by asking, why do we even need proof-of-stake? Or more precisely, what does proof-of-stake give us as protocol developers or blockchain developers? So the two main things that usually come to mind are, first of all, Sybil resistance. So I don't want anyone to be able to join the network, right? So that they can't overtake the network. So if I were able to sign up as many validators as I want, then I could just sign up an infinite amount of validators and then take over the network. So forcing people to stake some amount of money makes it harder for them to just set up an infinite amount of validators. And the second thing that proof of stake gives us, or the staking gives us, is the slashing conditions. And the slashing conditions are basically these situations where we want to punish malicious actors. Okay, so when someone behaves incorrectly, not according to the protocol specification, then we would like to be able to punish them for their malicious behavior. But proof of stake networks, they present a couple of really difficult challenges. Okay, so first of all, unlike proof of work, where theoretically users can generate their own tokens, with proof of stake networks, one of the main things you have to think about is the on-ramps. So how do users actually get your token? How do you get your token into the hands of users, and how can they buy it and purchase more of it so that they can stake it? That's the first issue. Second issue is that in order for users to want to buy your token and that token to have some economic value, meaning some price, you have to come up with some utility that creates demand for these tokens. And the last thing is that you need operators that run your network, that run the nodes on your network, to have enough conviction in your token that not only they would buy it, but they would also hold it for a long period of time, right? They would need to stake it. So shared security protocols like EigenLayer, they solve these challenges for us, because if you think about basically what they let us do is they let us reuse the ether that is staked by Ethereum validators in order to secure our network, our AVS. And that's really powerful because it means that we no longer need to worry about all of these things. So anyone can get Ether. Ether has very clear utility, and operators love Ether. Okay, not only they can stake it with us, they can even stake it with Ethereum itself. But it doesn't mean that the work is done. So there's a couple of other things that we still need to take care of. One, first of all, is what we would call the execution layer, and that's the logic of our AVS or of our network, like what actually happens as part of validating the network. The second thing is the consensus mechanism. So how do all of these different nodes that each of them can execute some sort of logic, how do they come to the consensus of which state or which result is actually correct? And another important thing that we need to take care of is the P2P layer, meaning how do these different nodes that are all over the world, they're spread out geographically, how do they communicate with each other, and how do we make sure that none of them are shadowed or eclipsed by malicious actors? So these are difficult challenges, and to see how that works in proof-of-stake networks, let's take a look at this diagram here. And basically what we see here is that when we are looking at the proof-of-stake network, we have a couple of different nodes. We have many different nodes spread around the world. They are all communicating with each other through some P2P layer. But if we zoom in on a specific node, what we find out is that actually every node is running two different clients. Okay, so for those familiar with how Ethereum validators work, so basically that's the usual way for proof. That's the usual architecture, let's say, for proof of stake networks to operate. And what actually happens is that each validator, each node runs two clients. One is called a consensus client, and the other one an execution client. Now, the consensus client is responsible mostly for communicating with all the other nodes through the P2P layer and receiving the different blocks or attestations that are propagated throughout the network. So the consensus client has two main responsibilities, basically. And that's, first of all, to set up the communication with all the other nodes through the P2P layer. And the second responsibility is to actually attest to certain results of blocks or transactions. So when we look at a proposed block, so for example, when a block proposer proposes a block, it first is received by the consensus client. Then the consensus client, what it does, it passes the block data to the execution client. Then the execution client, for example, on Ethereum, that's the EVM. Okay, so the EVM takes the block data, runs it, executes it, makes sure that the state transition is valid, and it responds to the consensus client with the answer of whether the block is valid or invalid. And the consensus client takes that answer and attests to it. So if the block is valid, it sends an attestation through the network. Now, if we look at AVSs, if we think of AVSs, they are very similar to proof-of-stake networks in the sense that they have this off-chain component that is validating some sort of logic, that's your AVS. But these AVSs, they also need to be able to communicate with the EigenLayer protocol. Okay, and there are many reasons. There's a couple of main reasons why you would want to, or why you need to communicate on-chain with the EigenLayer protocol. The first reason being that you want to make sure that all the nodes on your network, on your AVS network, they are actually staked with Eigen, right? Because if we identify malicious behavior, we want to be able to punish these validators or these operators. Another reason is that you would want to be able to distribute rewards to your operators, and rewards are distributed on chain, and you need to be able to interact with your operator addresses or accounts in order to send them the rewards. And slashing malicious actors, as we said before, that's why we want them to be staked. But the act of actually slashing them, that also requires an interaction with the EigenLayer protocol directly. The last thing that we want for our AVS to have on-chain is the component that verifies the task's validity. So we want to be able to verify that the attestations coming from our network are actually valid and not submit rewards or slashing, etc., if the tasks themselves are not valid or if the attestations are not valid. And last year is an optional step or optional integration is what you might want to do in certain cases is you would want to also interact with other external contracts. So just as an example, if you are building in a price Oracle AVS, you would probably want to, other than just validate or verifying the attestations, you would also want as part of every task or as part of the submission of these attestations, you would want to also update some contract with the price feed. So if we want to take this is a very simple overview of like what are the on-chain components that an AVS might have. And what we see here is that these attestations that come from arrive from the off-chain component, from our proof of stake network, from our network of nodes themselves. These attestations, they are submitted to a contract called AVS entry point. And this AVS entry point, it can technically be a single contract. It's usually made up of multiple different contracts in order to separate the concerns of each contract. But generally speaking, this AVS entry point, what it does is that it communicates with the eigenlayer protocols. So it can communicate with the eigenlayer slasher, with the delegation manager, etc., etc. And in addition, it can also communicate and interact with external contracts that you define. Okay. So if we take a look of an entire AVS and like all the different components, again, this is a very simple view, of course, but we have this off-chain part, which includes the task submission, the consensus, the execution client, and the attestations. And then we have this on-chain part, which includes the AVS entry point and the eigenlayer protocol. Now, what does the Othentic stack give you? So the Othentic stack gives you a couple of these components, and out of the box, these components can work and integrate with each other, and they also have the ability to be extended, the capability to be extended with your custom logic. Okay, so basically we have two of these main parts or the Othentic stack contains two main parts, which are the Othentic CLI or the Authentic node software. And the Authentic node software plays the role of a consensus client. Okay, so it includes the P2P layer and the communication, the attestations, the BLS signature, all of that stuff. And it communicates with some execution client. Now, this is an important part here. The execution client is your AVS implementation. So when you build on top of the Authentic stack, one of the things that you need to provide is the execution client. You need to implement your own execution client. Now, the way it works is that the Authentic node communicates with the execution client via some HTTP interface API or WebSocket or gRPC, etc. It's up to you. And the node software basically receives, every time it receives a task, every time it receives a task to validate, it passes it on to the execution client or the AVS execution API. And that execution API, it can be written in any language that you want. It can be written in Rust, in Go, JavaScript, Python, whatever you like, but it needs to conform to this AVS Web API interface, okay? So the AVS Web API interface is a set of endpoints that you need to implement, and that's how the Authentic CLI knows, or the Authentic node knows how to communicate with your execution client. Now, once a task is validated, the Authentic CLI will generate an attestation, and later on, it will aggregate all of these attestations using some BLS scheme, and it will submit it to a contract we call an attestation center. The attestation center is responsible for managing all of these tasks that come on chain, and it will interact with the eigenlayer protocol wherever it's necessary. In addition, it will also interact with these external contracts that you might have optionally deployed. Now, if we take a look at the on-chain part, so the Authentic stack utilizes the layer 2 architecture, the modular architecture of Ethereum by deploying some of the contracts on the layer 2. And the reason for that is that There's a couple of reasons, okay? So first of all, verifying the BLS signatures is a gas-intensive operation. So that's something that we would like to save costs on. If we would like to save the costs on that operation, we would run it on an L2, on the layer 2. Second reason for that is that most AVSs would probably validate tasks faster than Ethereum block times. So Ethereum block times are 12 seconds. Most AVSs would probably want to validate or perform tasks faster than that. And layer 2s, they have faster confirmations. And the last thing here is that this modular approach lets the Authentic stack support multiple different blockchains, different architectures, and different protocols. So that's another advantage of this design decision. In the off-chain part of the stack, what we have is the node software. Now the Authentic CLI, it can play a couple of different roles when you run its node software. So if you recall, we have a network of nodes. All of these nodes, they communicate with each other. They receive different tasks. They validate them. And at the end of the validation, once they validated these tasks, what they do is they attest to it. So each node runs an attester. Okay, so it's running as an attester node. And every attester node sends an attestation on the P2P network. And for every network, there's aggregator nodes, which are responsible for fetching all of these attestations, then aggregating them using BLS scheme, and then submit the BLS signature, the aggregated BLS signature, to the attestation center, which is a contract deployed on chain. All of that comes built in out of the box with the Authentic stack. So just a quick recap. So we have two main parts to the Authentic stack. We have the Authentic smart contracts. These include the L1 contracts, which are responsible for slashing and rewarding operators. And it also is responsible for registering operators. We will look at that in a second. And we have the L2 contracts, which are used to verify the attestations. And on the off-chain part, on the consensus part, so the Authentic consensus comes with a gossip sub-based P2P layer. It includes peer discovery. It does all the BLS aggregations, and it is extensible through the AVS execution API. One last point about Authentic stack is I want to emphasize what the Authentic stack is not, okay? So Authentic is an open stack, meaning anyone can use it, but it's not its own network, okay? So there is no Authentic network that is running. Authentic is not an operator, meaning Authentic, the company, doesn't run operators for you. And it's not an owner of any contracts. All of the contracts that you deploy using the Authentic CLI are your own contracts. They are owned by you. Okay? So you can think about Authentic as a suite of tools for building your own AVS network. Okay. Now, I'm going to show a couple of demos in a second, but before I do that, I want to talk a bit about what's called a task. Okay, so I've mentioned this term a few times here during this session. And I just want to go quickly over what a task actually means. So it's I hope it's not as confusing as it might be at first, but I will try to make it a bit easier to understand. So a task is basically a piece of data. Okay, so it can be a string, it can be raw bytes, it can be whatever you need it to be. That piece of data is propagated on the P2P layer, okay? And it's usually one of two things. So it's either the result of an operation, which requires validation by the network, such as a block, or it's the request to perform an operation, such as, for example, a transaction, okay? So when I have a block proposer proposing a block, what happens basically is that that block is propagated throughout the network, and then every node goes over that block, runs it through its EVM, through its execution client, and validates that the block is actually valid. And the other example is for when if I was a user and I wanted to, for example, make a swap, okay, so I send a transaction to the network, the transaction is propagated through the network, and each node executes that transaction. So the task in that case is the transaction itself and the data for that transaction. One other thing to note here is that AVS networks could have multiple types of tasks. Okay, so you're not limited to a single type of task. Just as an example, let's go over the AVS sample that we have in the workshop document that I'm going to show in a second. And also, I think there will be in the show notes, there will be links to the workshop document. Feel free to go through there and just follow the instructions there. Please note that all of the tooling that you will see here are right now in beta access. So you have to, we have a form where you can request access to the beta, and we will give you access to that so that you can use the tools. So the AVS sample that we are running in the workshop document, in the workshop flow, is a price validator AVS, which basically means it's an AVS that validates the current price of a certain asset. So how would how would a task look like, or what will be the flow of a task like that in an AVS like that? So basically we have an entity, let's call them the task performer. Now the task performer, what they do is that they contact some price feed API. They check the price of a certain asset, let's say Ether USD, and then they want to validate the price of that asset, so they send it to the AVS network for validation. Every node in the network receives the price data that the task performer fetched. Okay, so if the task performer saw that the price of Ether is right now $3.8 thousand, then it sends that price to the network. The network, basically what it does is that it looks at their own, each node in the network, what it does is basically that it looks at their own price feed. Okay, so each node, along with the execution client, it also has the ability to contact their own price feed. And what they do is that they check their price feed and see if the price is similar or equal to the price that the task performer reported. Now, every node does this validation, and every node attests whether the price they see fits or matches the price that the task performer reported. If it matches, then they attest truthfully to it, meaning that the task is valid. And if it doesn't match, then they attest to the task as being invalid. Now, the task performer sends their task to every node in the network. Every node does this process for validating whether the task is correct or not. And at the end of that process, each node sends its attestation to the aggregator node that we saw previously. And the aggregator node will aggregate the attestations, and if there is a consensus by 66% of the voting power or more, it will submit that task on chain, and the task performer will either get the reward or will get slashed if their task was invalid. So hope that helps make it a bit clearer what a task actually is. So I'm going to move into showing a couple of demos. I'm going to show a couple of videos, and I'm going to explain what we're seeing as we go through them. I will pause here and there just so I can talk about specific things. I will also skip over different parts because we will not necessarily want to wait for all the different commands to run to completion. But I will just try to do this quickly, and then after these videos, we can move on to questions if anyone will have some. Another thing, by the way, is that you can use these videos. The idea is that you can use these videos when you're working on your hackathon project. Use these videos to see that if you're following the workshop document, you can use these videos as reference to make sure that everything is working well, that you get the correct output, and that everything is going as it should. So usually we start by installing the Othentic CLI, and the Othentic CLI is it's an npm package. So you just install it with npm. It runs here. I'm gonna skip all the dependency installations because it's not interesting, but you get the idea. Now, once you've installed the CLI, we clone the AVS samples repository, and the AVS samples that contains the logic for our sample or for our demo AVS. And then we create a .n file with a private key in it. And that private key, it will be used to deploy your contracts. Okay, so that's the private key used for deploying your contracts. Just a second. Okay. Next step is to actually deploy your on-chain components. So we do this again with the CLI. We run the network deploy command. And the arguments you see here there are 3 arguments here. So the ERC20 flag basically means this is the reward token that you will use for your AVS, for your operators. This is the token that your operators will receive as reward. You can choose whatever token you want. This one, I believe, is USDC on Amoy, I believe. But it can be, for the purposes of the demo, it can be any address, because as part of the demo, we don't distribute rewards. The 2 other arguments here are the initial deposits into your contract. So 1 Ether on Holsky and 2 Matic on Amoy. By the way, by default, the Othentic CLI deploys on Amoy and Holsky. You can also configure it to deploy both contract sets on Holsky on the same layer. Okay, so that's an option. We usually recommend deploying the BLS verification contracts on a layer 2 just because it's more expensive. So what happens here is you can see we're running a couple of different commands. The contracts are written using Foundry, so we deploy everything using Forge. We run a couple of scripts here. So first we deploy the layer 1 first we deploy the layer 2 contracts, then we deploy the layer 1 contracts, then we perform some activation for these contracts on each layer separately. And eventually what we get here, if I'm gonna skip ahead just a second, at the end of the deployment, what we get is we get this list of contracts, and these are all the contracts that are being deployed. Again, they are deployed by your own private key that you've inserted in the .n file, in the .n file. Now, the contracts that we have here, I'm not going to go over all of them. I'm just going to go over the interesting ones. So the ERC20 we covered already. That's the ERC20 that you provided in the initial deployment command. The AVS governance is the mainnet component. This is the component that communicates directly with the eigenlayer protocol. The Vault contract, this is the contract that is responsible for keeping and distributing the rewards for your operators. And we have this message handler contract here, and this contract is responsible for communicating with the other layers. So we have 2 of these contracts. So we can see that we have the L1 message handler and we have the L2 message handler. Now these 2 contracts, they communicate with each other cross-chain, and they pass different messages along. I'm not going to get into all the details of what messages exactly they pass. But on the L2, the main contract that we care about is this attestation center. This is the contract that verifies all the BLS signatures. So that's an important contract. Next, just a second. Okay, so next, once we've deployed our AVS contracts, the next step is now to register operators. Okay. So in order to register operators, we again use the Othentic CLI. We use the operator register command. We provide a private key, and we provide the address of our AVS governance contract that we got in the previous step. Okay, so in the previous step, we had the AVS governance contract in the final output. We take that contract, we insert it here in this command, and we can register our own operator. I will go through the steps that this command performs. Basically, we have a couple of different steps here. First of all, we check whether you have STETH or STETH. in your account, because that's necessary in order to delegate on EigenLayer. So if you don't have some stETH, then this command will ask you whether you want to convert some of your ETH to stETH, and then it will stake it through the EigenLayer strategy. It will send it to the other EigenLayer strategy through the EigenLayer delegation manager, and basically that's the stake that your operator will have. That's the voting power that your operator will have as part of the network. Now, what you could also see here is that there's a couple of questions that you need to fill in. So you have the operator name, you have the description, website, etc., etc. These are details that will appear on the EigenLayer UI. Okay, so you should, when you're registering your operators, or when your operators register their operators, then they should provide these details so that users will be able to recognize and know which operator is which, and know whether they can trust them. So here, for the purposes of the tests, I'm just inserting some different strings, different names and descriptions here. It doesn't really matter for the purposes of the demo. What you can see here at the end is that we're also uploading this metadata to IPFS, and the IPFS is linked to the EigenLayer UI through their smart contracts. So that's another important step to know. And again, you do this all through the Othentic CLI. And once we've registered our operators, so I will just quickly summarize what we did up till now. So we installed the Othentic CLI, we deployed the network with a single command, we registered an operator. By the way, in the workshop document, we register 3 different operators. Okay, so in order to run the AVS example, we need 3 different attesters. So we register 3 different operators, and then we run 3 different attesters using a Docker Compose file. And that's what I'm going to show you now. This is the entire network running on my machine, and you will see the logs here they run pretty fast, but I will pause here and I will explain a bit what happens at each stage, and then you can see whether, when you're running your own AVS, you can use this as a reference. So basically what's happening here, and I'm going to go back here. So okay, so here what we can see is that the AVS attesters, they are starting to connect with each other. Okay, so this is a Docker Compose file. For those who are unfamiliar, Docker Compose lets you run multiple services all at once, and they can all communicate with each other on the same network. So what we have here, we have 3 different attesters. They all connect to each other once the process starts. Then we submit a task, and there's an explanation of how you can submit the task to the AVS. We do it through through an HTTP request. It's in the workshop document. You can see exactly how to run a task on this AVS, but basically it's a manually triggered task here. So we trigger the task, and then we can see that the task performer is executing the task. It sends it through the network, and we can see all these new message received. Okay, so these new message received, we can see, so we have a tester 1, a tester 3, and a tester 2. They all received this new message, and now they're validating it. So they are all communicating with this AVS Web API container, and this is the execution logic of our AVS. So the execution logic here, again, if you recall, as I explained previously, this AVS, what it does is basically it's a price validation AVS. Okay, so it validates that a certain endpoint price feed is accurate. Okay. So what's happening here is that each node on the AVS network gets this task, gets the price feed as the task performer reported it. It contacts the AVS Web API, or the execution logic, and it receives its own price feed, and then it compares it to the price reported by the task performer. If the price reported by the task performer is accurate, then the task is valid. And as we can see here, all of these nodes, they approve this task. So once they approve the task, they start signing, and we can see all of the nodes signing separately. And eventually, the aggregator, which we can see here. Oops. One moment. So the aggregator, which we can see here, okay, is now aggregating all of the tasks. So it goes it's aggregating all of the attestations. So it goes one attestation at a time, and one by one, it aggregates it into a BLS signature, and eventually it submits it on chain. So it's difficult to see it here in the video because it cuts off exactly as the task is submitted on chain. But when you run the demo locally yourself, you will see that there is another message here by the aggregator stating that the task has been successfully submitted on chain. And I can tell you that all these videos that I recorded them separately, okay? But it doesn't take much longer than that to actually deploy your own AVS and get it up and running. Usually we do these workshops within under an hour, 45 minutes. People already have their own AVSs deployed, and they can start playing with them, changing the code. All the code is open on our AVS samples repository, Again, it's currently in beta access, but if you request access, you will be able to see all the code for the samples, and you can change it, you can copy it, you can change it, you can start, like if you're starting your project from scratch, then you can use these samples as a starting point. And basically, that's it. It was really a pleasure being here. Thank you, DoraHacks, for hosting us. Thank you, Jan. Thanks all of you for coming and watching. And please talk to us. Okay, so if you're planning on building an AVS, planning on building on Othentic, talk to us. We have our website. You can contact us there. The docs website has all the information that you need, and more detailed than what more detailed information than what I just presented here today. And if you want access to the Othentic CLI tool, then please request access through the form. This is the beta access form, and we will give all of you access to our tools. Yeah, that's it. Thank you so much, and good luck with all of your projects.
Yotam, so thanks a lot. There's this one question from the audience about the form that you just mentioned. So like how they can like apply, if they can just have an idea or like if they need to build a project.
Yeah, so if you want beta access, just simply write us that you're that you're working on the DoraHacks hackathon, and we will just give you access.
Okay, that sounds
basically
great.
anyone, just to make it clear, anyone here is welcome to ask for access through the form. Okay.
And maybe one more question before we end this one. So what would you like to see that developers are building at this hackathon?
Yeah, that's a great question. So there are many different ideas for what AVSs you could build. I think there's a couple of really interesting ideas floating around. You can find them on Twitter. I see Eigenlayer themselves, they sometimes drop all sorts of ideas. I do think that there are a couple of interesting AVSs to develop in areas of DeFi. And so, for example, solver networks are a very popular example. So for those of you who know CowSwap or Uniswap X, those services, so you could build an AVS that does that, and you could also build an AVS that does that very efficiently and in a very decentralized way. So that's really cool. Another thing that is a very popular option is a very popular AVS is off-chain computation. So think like chainlink functions, for example. So an AVS that lets you send a transaction on chain, and then the network picks up the transaction, performs some action off chain, for example, get the price from some price feed, or perform some off-chain computation like zk computation or anything like that, and then submits the results back on chain to the contract that requested the data. And that could all happen through an AVS in a decentralized way. And with the Othentic stack, it's relatively simple to build something like that. I think these are two good examples, but I do also believe, by the way, that we do have, I'm not sure if it's on the website or in the workshop document, but we do also have a couple of pointers for people who are planning on building an AVS, a couple of pointers for and ideas for what they can build and how to build it and stuff like that. I will make sure to share it. If it's not on the website, then I will share it through the document, the workshop document. So check out the workshop document to see more details about that.
Yeah, like the link to the workshop document is also in the YouTube comments. And I would be also super excited to see some off-chain computation, AVS, or a solver, or like something that's intent-based. Super excited about those things and beyond. So thanks a lot for your time today. Thanks a lot for your contribution. Would you want to like add anything else before we wrap it up here?
No, just talk to us, follow us. You can follow us on Twitter, 0x at 0x Othentic, where we share updates. We also share updates about projects and teams that are working with us. And generally speaking, we are really happy to meet and talk to people, projects, users that plan on using the Othentic stack, and we would like to help. So reach out.
Okay, perfect. So thanks a lot to Yotam from Othentic for joining us today and contributing your time and efforts. I think it was a super insightful workshop about how to deploy an AVS using the Othentic stack. So guys, if you have like any questions, feel free to try their product, to join their community and engage with the team. I think they're also like more than happy to get to know you guys. And yeah, so thanks again for joining us today. Hope
Thanks
you guys build the next incredible product that onboards the next billion users, and see you next time.
Bye, everyone.
Thank you. Bye-bye.